heb het niet weten. Het gaat een uurtje, maar ik wil even chillen.
Maar ik zou het zelf gaan organiseren. Ik zie dat niet, maar ja, ik kijk wel.
Jo. Ja.
En ik dacht dat ook, maar ik dacht helemaal niks.
Niet te donker? Maar dat is oké. Ik kan het tenminste zien.
Hij zit er niet in.
Jij bent niet de meeste op de zit.
Ik was bezig met de nacht en de meeste
Ja, dus
verder in
links van die gang uit, moet je in plaats van naar beneden gaan, dat zijn dat stuk boven de ja, de studio. Net voor de studioadviseurs in deze kant.
Deze kant.
Okay, welcome to the 8th lecture on multibody dynamics. I'm not in such a good mood after last night. Oh my gosh. Second half I was sitting like, okay. Well, let's not talk about it, right? Multibody dynamics. Another multibody dynamics topic. Yeah, let's start with a quiz, Kahoot. Okay. Kahoot. My Kahoot. Number 8. Yeah, looks good. Okay.
Dus ik kan het aanpassen. Hij deed het wel. Hij deed het toen. Dat is best wel.
Okay, 109 players in the field, 110. Let's start. Again, 5 questions. Yeah, please discuss, huh? You don't have to whisper.
What's the minimum number of cuts for administrative issues? Ja, 2. Waarschijnlijk is het op 2. Ja? Ja, iedereen meteen.
Bent er niet helemaal bij. Na gisteravond.
Ik ben ook even iets langer blijven zitten.
Ik had het ook.
Ik niet. Ik was Multibody aan het doen.
Yeah, okay, that was not so hard, right?
Het was eigenlijk een beetje dezelfde soort.
Okay, time response of the system.
Ja, dat is dezelfde als de opdracht.
Please discuss, huh?
En energy conservative.
Ja. Nee, wat daar. Ja, er is geen.
It's none of the above. Want het is en energy conservative en periodic.
Ja.
Chaotic is volgens mij niet gezet.
Voor je vandabel.
Yeah, okay, super. Convergence rate of the Gauss-Newton process, the coordinate projection method. Don't read the text, it's just to illustrate that it's about the Gauss-Newton method. I mean, you can look it up. There is Google, there is your neighbor, there is a book, there is...
Er is een... Ja, dat... Maar... Het is sowieso een jaar met strategie realiseren.
Oké, je moet het kiezen.
Oh, ja. Wat? Ik ben kut. Ik wil ervoor verder.
Nou. Ja. Iets met elektroden of zo, ik weet het niet. Ja, so that's a bit disappointing. And it's because I'm asking a little bit next to the field. I didn't talk about it during the lecture, but when you did the homework assignment and when you used the coordinate projection, you noticed that the convergence rate was pretty fast actually. The number of steps, I mean sometimes 1 or 2 iterations. And if you look into the literature, it's clearly that the Gauss-Newton process is a quadratic process. because you linearize the problem, and well, you can read all about it on the internet or whatever. Okie doke. LSA? ISA. Oh, yeah. No ISA? Okay. The C plus matrix. What is the C plus? Now you have to read.
Ik weet zeker dat hij van pseudo is. Het staat hier.
Ja, het is gewoon, ja, het staat hier zo ergens. Ja, maar hier staat ze dan hier. Ja, het is veel.
Please check all the answers, hè?
Maar ik heb dus nu een boek
Maar is het dan een matrix? Ik twijfel of het zo gedaan wordt.
Ik heb 20 euro betaald voor spelfouten. Om even door te sturen over Ajax.
Dat is wel jammer. Maar ze waren inderdaad wel echt zelf aan het lopen.
Buikpijn.
Yeah, that was an easy one, right? Actually, there were two correct answers here. The official name is the Moore-Penrose Pseudoinverse. So it's connected to two persons, Moore and Penrose. Read all about it. And in MATLAB, the command to use is this is pinf, pseudo-inverse. You can also use backslash, but backslash is a little bit more smart. It sometimes does other things. So if you want to be sure about pseudo-inverse, use pinf. Chris, are you here? No. Okay, last question already. And it is about today's topic. You have 90 seconds. So just read and think and discuss. It's this, right?
De afstand en de hoek.
Ja, dat denk ik, ja.
Dat is 2.
Ja, dat denk ik.
2.
No discussion?
Oké, ja. Ik denk is. Maar dat, ja, dan moet je dus eigenlijk van de positie. Nee. Misschien echt iets.
Steeds helemaal niks aan. Ja.
Yeah, okay. So most of you have the correct answer. It's 2. There are various ways to come to 2. There is, of course, the intuitive way, the religious way that you believe. Well, the thing which is modeled is something like a bicycle, right? And if we talk about the bicycle can be put anywhere in space, right? So you can have x, y coordinates, and the angle can be anywhere, and the steering angle can be anywhere. So it has and the wheels can have any rotation. So there are a lot of degrees of freedom kinematically in the coordinates. But if you talk about motion, then the only way you can move a bike is, of course, an upright bike, is going back and forth and steering. I mean, that's all you can do. So if you want to go to some other position in another orientation, then you have to do some complicated parallel parking trick to get your vehicle there. So although kinematically in the coordinate space you can put it everywhere, at every configuration, you cannot easily move there. You cannot move sideways. It's impossible. Okay, that's the topic of today actually, the rolling contact or non-holonomic constraints. So let's save the results. Good work, Chris. Download.
Je zei ze vorige week volgens mij niet op Brightspace gekomen.
Let me first finish this. Thank you for the feedback. There was a question in the audience. The grades for what?
For last week Kahoot.
Oh, did I forget? Oops, sorry.
Yeah, because Kahoot was not working.
No, it worked well. I checked everything and it was okay.
Okay.
I did all the math and then the calculation, and apparently I forgot to upload. I will do this afternoon together with it today. Yep.
That's fine.
Okay, save the results. Code is there. The thing is running. Here we go. Yeah, that's good. Okay, let's go to today's topic. This is all jiffy. Okay, picture a wheel. And then, I would say picture a wheel which rolls without slipping. Without slip. And since we still live in a two-dimensional world, we only think about two-dimensional. But I like to draw a 3D thing to really show, it's a wheel which is rolling. But it's rolling on a plane and it's always staying upright. That is the idea. So it has some forward speed. And of course, it also has some rotational speed, right? Of course, the wheel has a radius. And now we do just upright. Upright or sort of 2D. It's a semi-2D because there's also this other rotation which is not in the z direction. So let's look at this projection in 2D. Then how does it look? Well, we draw our coordinate system, x and y, with our origin. And then we have the wheel somewhere located in space, right? This is the center of the wheel at some angle. So this is the orientation, phi, and it's located at some position, x, y. But the velocity of the wheel in general can be in any direction, right? Well, not in reality because we don't want slip. But if we say we do not want slip, we have to express what is slip if we have some velocity. So let's, for Pete's sake, just say, well, the velocity is like this. So the v, velocity vector, x dot, and y dot is like this. Of course, it doesn't comply. My v's are not so clear. It doesn't comply with non-slipping, but for now we just take this general case. I have the direction of the wheel, that is this vector, and I have the one perpendicular one, which is the axis of rotation actually of the wheel. So I draw that one, say that it's perpendicular. So all rotation is this beta dot is about this one. And now if we look at the picture, we can project the speed on the longitudinal direction and on the lateral direction. So we do the projection like this and like this. And we have a speed component here and we have a speed component here. Let's give them names. I call this the v in the direction, and this is the v perpendicular. Okay, the wheel has a radius r. I forgot to put that in. Yeah, so that is the complete picture. Now what we want is, of course, that this speed is 0. Then the thing is, has no lateral slip. And then, of course, we also have to connect the rotational speed and the radius with this forward speed. So there actually are two conditions. One is that we don't want the wheel to slip sideways. That's impossible. And if the wheel is moving in the right direction, then we want this rotational speed of the wheel comply with the forward speed. So it's two conditions actually. Okay. So what did I say? Conditions for pure rolling. Conditions for pure rolling are no side slip, which we just say that this V perpendicular just should be 0, and it's and then pure rolling. That's not a P. Pure rolling in the forward direction, I said. And forward has to do with the geometry, right? Not with the speed. So forward is defined as geometry forward, which means that this V forward is beta dot times R, and plus or minus, what is it? Plus or minus with a plus. A lot of errors always happen by plus or minus. I get questions on WhatsApp about the homework, and if I have time, I answer them. And most of the times it's a plus or a minus error. Oh yeah, I put the force in the wrong direction. Okay, but this should be right. Now these conditions, they are not on the coordinates, right? These conditions are on velocities. And together, of course, with the coordinates, because it has to do with some configuration, but still they are on the velocities, and we call them with a funny word. I think it's a funny word. Non-holonomic constraints. Holonomic constraints. And apparently, so you also have holonomic constraints, and read all about it. Heike made a very nice overview of all the nomenclature in constraints, scleronomic, and I don't remember, I don't know. That's her thing. And apparently there are also holonomic constraints, but also non-holonomic. Now, non-holonomic constraints, this funny word, was actually pitched by Heinrich Hertz. So Heinrich Hertz was the first who really defined this. Before that, people had an idea about pure rolling and so on, but Heinrich Hertz really dived into the mechanics, the basis of mechanics, the basic theorems, and in that discovery also classified these type of constraints. So he was actually also the first who was looking at these rolling contact problems in a systematic way. Before that, of course, the rolling disk had already been analyzed, but those were very special cases. He wanted to go to a more general case. Okay, now let's be clear about how does it work in our problem. So I need actually this picture. Yeah, how am I gonna do that? Yeah, so I need this part approximately. So copy, and then we go down here somewhere. Put it here. Yep, that's okay. Go back to 100. Otherwise, 100. Yep. No, what did I do? This can be a little bit smaller. Yeah. But general must be 100. Yeah. So this is the layout again. We have these conditions, right? No side slip and no forward slip. So now, with this picture in mind, let us write them down. So the V, no side slip, V perpendicular should be 0, breaks down in our case as, well, this scalar quantity is of course the result of a projection, and in our case it's a projection of the speed on a certain direction, and the direction vector is of course, well, this vector at an angle of phi. How did I call that? I didn't give it a name. Well, actually I want to have the one who is perpendicular to this one. I want to have this direction, Well, looking at the picture, the direction is clearly that the x component is minus sine phi, and the y component of this vector is cosine phi. So the dot product of the velocity with this direction, that should be in the lateral velocity, and that breaks down with v being this x dot y dot as minus x dot sine phi and plus y dot cosine phi, right? And that should be 0, and that is our constraint. So that's the first constraint. Then the second one, the one where we say it should be in the driving direction, in the forward direction should be beta times r. Well, again, we have to write down what is the driving direction. So v, driving direction is v dot, v with a dotted with the driving direction, which is now super simple, cosine phi and sine phi. And that then breaks down to simply x dot cosine phi plus y dot sine phi, and that should be equal to beta dot r. So this is one constraint, and this is another constraint. So those are the two constraints. Note that we have an extra coordinate. And that is a bit strange, of course. It is extra coordinate beta. It is rotation about the wheel axis. So it's like a 2.5D problem, something like that. Yeah, we could say 2.5D. We're doing 2.5D. So the coordinates of our system, if we have to write it down, we say, well, that is x, that's y, that's phi, and now we also have this beta for the body. Just an extra coordinate. I will come back to that in a minute. Now let's focus first on side slip. So focus on side slip. So then we don't have to deal with this extra coordinate. And so this v dot should be 0. Now, what was the expression? V dot was x dot with a minus sign, right? Yeah, times sine phi plus y dot cosine phi is 0. Now, like in all the other constraints, we just give it a name, and then we say that thing should be 0. So we define now side slip as S1 is equal to minus x dot sine phi plus y dot cosine phi. And then no side slip is simply S dot is 0. And if we only look at such a system, you could say, oh, this is like a skate, like in a skate. So forget this whole beta stuff and this forward rolling and so on. A skate, which you can draw something like this, can only move in this direction. So there is no rotation, it's just like your skate on the ice. If you put your skate on the ice, you cannot move it sideways. You can only move it in the forward and aft direction. And of course there's a little bit curvature, so if you apply a torque during motion, you can steer a little bit, but technically a skate can only move back and forth. So it's something like this, the skate thing we're now focusing on. And then if it has this speed v, which is not in line with the skate, then we have this side slip S1, which should be 0. Now, formally we can write that very nicely in the same way as we do constraints. We can say, oh yeah, S1 is some capital S1I times x dot I, and that should be 0. That's a very general formulation of such a constraint. Note that I have written a velocity constraint linear in the velocity. Up till this day, we are not aware of any non-holonomic constraint which is not linear in the velocity. So all kinematic non-holonomic constraints are always linear in the velocity. We don't know about any other way. I mean, you could say, oh, you put v square in it, or cosine whatever, omega dot, or omega, angular speed. No, it's always linear. So we can write it down then, of course, in a matrix vector form. So in our case, it's with R. I dropped now the beta because we're only looking at the skate. So this is then the constraint equation. And then here I have minus sine phi. I have here cosine phi. And I have here 0. So S1. Now, this is of course the constraint on the velocity. And then the constraint on the acceleration. Constraint on the accelerations, which we finally need in our equations of motion, are then, well, you just differentiate the thing as S dot 1 equals, we can use this expression, for instance. We first keep this constant and we differentiate this, so we get minus S sine phi cosine phi 0 times, and then we get x dot y dot phi dot, and then plus, and then we take the derivative of these guys. Note that there is no x and y here, there's only phi here. And so then the term we get is, if we differentiate this to phi plus phi dot is, let's put a square bracket, we get minus cosine phi dot x dot, right? That's the first one. And the second one is minus sine phi dot y dot, and then the third is 0. That's it.
The previous velocity vector needs to be double dot, right?
Yeah, absolutely. Thank you. Oops. Now, I'm going to rewrite this a little bit. I'm going to rewrite it like this because it's a double product of velocities, right? And it's a scalar thing, so I can write it as the following thing: x dot y dot phi dot transpose times a matrix times x dot y dot phi dot. And sometimes this is called the Hessian or something like that. And then I just have to pick all these numbers. And if I do that, then the conclusion is it looks like this: minus cosine 0, 0, minus sine phi, and 0, 0, 0. Or in other words, you could also read this as this is so this guy we know called S1I, right? Times x dot I, double dot I. And then here we have plus S1I comma j x dot I x dot j. We call these terms, of course, convective terms, right? Remember from the normal constraints, we also all these things quadratic in the forward speed, we call convective terms. Or in other words, we say h1 is minus x dot phi dot cosine phi minus y dot phi dot sine phi. Now, why do I go into all this deep trouble? Because you would think, well, if this is a velocity on the constraint, maybe I can pull it up one higher level and just write it in terms of the coordinates, right? And then we can apply all our standard mechanisms and theories for constraint equations of motion. Well, it turns out you cannot. What I have written down here is a differential equation for which there is no primitive. And how am I going to show that? Well, let's assume that there is a primitive for that. Yeah? So let's assume that you have some function f from xi, yeah, which is the integral of S1 with respect to time, of course, in our case. Then, of course, by definition, this S1 is this f. Yeah, I have to give it the name 1. F1 comma I times x dot I. So then this thing which we derived, this, what was it? Minus sine phi cosine phi 0 times x dot y dot phi dot. Then this thing is a derivative of some primitive function. If that would be true. Well, then if we continue, then we get S dot 1 is then the F1I x double dot plus the F1ij x dot I x dot j. We know that from differentiation for this guy that F1ij should always be identical to F1ji. The order of differentiation doesn't matter in functions. However, if we look at this matrix, we see it's non-symmetric. Whereas here we come to the conclusion it should be symmetric. So we have a conflict there. So it cannot be true that there exists some primitive function from this non-linear, from this non-holonomic constraint. So the conclusion is I write down a differential equation for which there is no primitive. So I cannot go up to a higher level. That's it. I have to stay on this velocity level. And that's why we classify it as a special constraint. We call it a non-holonomic constraint. Okay, so the conclusion is a non-holonomic constraint is a one on velocities for which there is no primitive. Now, and of course we have the other constraint, the S2. We can treat it in the same manner. I think it's written in the book. For now, I don't find it so interesting. You'll get the same non-symmetric second derivatives, or in this case third derivatives. And again, you come to the conclusion, oh, even this condition of rolling forward, with pure rolling in the forward direction, is a non-holonomic constraint. So the two constraints I wrote down, S1 and S2, are both non-holonomic constraints. The next step is, of course, how do we incorporate this in our dynamics system? Because we know how to do it with holonomic constraints. So we have Lagrangian multipliers, and we put that in, and we differentiate the constraint twice, and then we set up the big DAE. So we want to do that for this case too. So the next step is deriving the equations of motion for a non-holonomic constraint system. Non-holonomic constraint system. Okay. Well, it of course starts with. Where does it always start with? Deriving equations of motion. Bad luck. Still 10 minutes. How do we derive our constraint equations of motion? What was the start? Virtual power, exactly. So just write down your virtual power expression. That's always true. You have applied forces, you have mass, Mij, you have accelerations, and you have virtual velocities. And these should, if this is 0, for all virtual velocities, I write down in words which fulfill, and I never forget where the double L's are, which fulfills the, that is fixable. That's fixable. That is fixable. Some glitch, or I don't know. Or maybe I pressed the wrong button. Who knows? Oh, we have some extra nice thing. Oh, I can get rid of that maybe. Did I get it? Item picker, this guy, go away. Yo! Okay, 100%. So for all the virtual velocities which fulfill the constraints, right? That is the statement. Then the system is in dynamic equilibrium, and meaning we get our equations of motion. So now we have to add our constraints. What are our constraints? So in a general manner, I would write my non-holonomic constraints like this: non-holonomic, holonomic, constraints as sk, meaning ski x dot I is 0. Now, a smart student would think, oh, hey, this looks almost like a normal constraint and it's already differentiated. So, you know what? Virtual slip should be 0, or in other way, I can just put virtual here, and now I have my condition on my virtual velocities. And then again, you take the standard machinery made by Lagrange. I put it in with a Lagrange multiplier into the equation. So I make a delta P star. And I say, well, I have my Fi minus my Mij x double dot j times lambda. And then what do I never know if I do plus or minus. Let's see, what did I do? Minus, okay. Minus, well, lambda k, our unknown Lagrange multipliers, times these virtual velocities. And that should be 0, yeah, for all these virtual velocities, which can, for all these virtual velocities, which then can be written like, we have these constraints. And they should not be all 0, of course. So let's put then this expression into the virtual power expression. So we get delta P star, our applied forces, our generalized mass matrix. And we want to write everything in terms of these virtual velocities. So we get ski virtual x dot I is 0. Yeah, and now it holds for all virtual velocities as long as they're not all 0. Well, if that is the case, then you take as a virtual velocity first 1, 0, 0, 0, you get the first equation. Then you take 0, 1, 1, 1, 0, 0, second equation, 0, 0, 1. Of course, you could also do other things like combining equations. I mean, if you have two equations of motion, adding them up is also an equation of motion. That's a perfectly valid equation of motion. It's not very useful at the moment, but so that breaks down to I equations of motion. I EOMs being Fi minus Mij x double dot j minus forgot a k, lambda k ski is 0. This system, and of course, we have to add the constraints, plus these constraints ski x dot I is 0, but we have to go to an acceleration level for that. So we write then skj x double dot j plus skj l x dot j x dot l is 0. So this set plus this set then forms our whole set of equations for the non-holonomic system. Or in a pseudo matrix vector form, we get then this. We have here, of course, the mass matrix, Mij, x double dot j. Here we have our multipliers. And then we have here our ski. And then on the right-hand side, we just have our applied forces. And then this equation you have to put in here. It already has a j from here, so that was good. Skj. Here we have a lot of zeros, kk zeros actually. And then on the right-hand side with a minus sign, skj, comma I, x dot j, x dot I. And that is it. Then we solve this stuff. Of course, we have to do a small trick because the speeds we get after numerical integration are not completely correct. So we solve for the acceleration now. Solve for x double dot j, and for free you get these forces, these constraint forces, which we can interpret it very nicely, because if this is the wheel and it may not slip sideways, then of course the constraint force we find here is just the lateral force in the contact point. So, clear interpretation of that. So, having this, then we do our numerical integration. Numerical integration step. And how did that go? Well, xn plus 1 was xn plus x, yeah, I sometimes write this numerical x dot n dt. And the same for the speed. The speeds are the old speed plus the numerical integral of x double dot n dt, which we get from here. And this is just a state vector. Now, the new coordinates, the new coordinates xn plus 1, they are okay. I mean, there are no constraints, so that should work. There is no coordinate projection we have to do, at least if you have a system with only non-holonomic constraints. Then these new coordinates are what they are. I mean, the result of the numerical integration step. However, the new velocities, x dot 1 plus 1, they are an estimate. And the big question is, question mark, do they fulfill the constraints? Do they fulfill, and the constraints we can write down, ski x dot, and then I n plus 1 is 0. And you have to check that. And usually, of course, they don't, because it's a constraint, so there will be a little bit drift. And again, with the coordinate projection method, or with the Gauss-Newton process, Gauss-Newton or coordinate projection, we can get the whole stuff back to 0 on the surface. That is no problem. Did I write it out? Yeah, I did. So, you could say I have already, of course, a linear equation. So I could say, well, the correct x dot is the approximate x dot plus a delta x dot, right? And I can multiply this, of course, put this in my constraint equation. So then I get my well, let's put an index there then. Ski times my x dot I should be 0, or in other words, I get my ski times my approximate value plus my ski times my delta x dot I should be 0. And clearly you see you want to solve from this set of equations what is my delta x dot. So ski delta x dot I is in this minus. And this is of course the error we have, right? And this thing is the error in the constraint. And we have exactly the same process. But since this is a linear process, you can solve it in one way. You can immediately say, oh, my delta x dot I is, oh, I can now use the S plus, right? Shall I do that? Yeah, why not? With my, what was it? SKI plus times this error. And it's just a one-step thing, because after this, it's immediately on the surface because it's a linear problem. Okay, let's take the coffee break, and then we're going to do an example of such a non-holonomic system.